Imagine fitting a world-class, video-analyzing AI right onto your smartphone, simply by teaching a text bot how to see. Well, Tencent's new Penguin VL just made that sci-fi dream a reality. Welcome to our podcast, Artificial Intelligence, papers and concepts curated by Dr. Satya Malik and narrated using AI-generated voices. We are thrilled you're joining us today for a deep dive into the Penguin VL technical report by the Tencent AI Lab.
Yeah, thanks for having me. The mission today is really to understand exactly how these researchers built this highly compact, incredibly smart vision language model.
Right, by completely flipping the script on how artificial intelligence, sees the world.
Exactly. It really is a paradigm shift. We are finally moving away from that brute force method of just making multimodal models bigger and bigger.
Yeah, just throwing more compute at it.
Right. Instead, the Tencent team looked at how to make the architecture fundamentally smarter from the ground up, basically avoiding that massive parameter bloat we usually see.
Which is huge, because the compute cost of these massive models is, well, it's keeping them out of the hands of so many businesses.
Oh, absolutely.
If you want to run a vision model locally on an edge device, like, say, a smartphone or an autonomous robot navigating a warehouse, the infrastructure costs and latency issues are just a nightmare.
Yeah, you simply can't deploy a massive server rack model onto a tiny local device.
Exactly. And actually solving that barrier to entry is something today's sponsor, BigVision.ai, works on daily. This podcast is sponsored by BigVision.ai, a consulting and product development company that helps companies of all sizes build computer vision and AI solutions. You can reach them at contact@bigvision.ai.
And that deployment challenge at the edge, that is the exact friction point the Penguin VL architecture aims to resolve.
Right.
But to really grasp the magnitude of their breakthrough, we kind of have to examine the structural flaws in the status quo first.
The way everyone else is doing it right now.
Yeah. The prevailing practice in multimodal development is to initialize the model's vision encoder using massive contrastive pre-training.
So we're talking about bolting on established vision heavyweights,
Right.
like CLIP or SIGLIP as the foundation.
Right, exactly.
But the paper calls this out as an objective mismatch. I mean, if contrastive learning is just pulling matching image-text pairs close together in a high-dimensional vector space and pushing non-matching ones apart, you are optimizing purely for discrimination, not actual comprehension.
Precisely. Mathematically, to achieve that really broad separation in vector space, the model is heavily incentivized to discard localized patch-level information.
Oh, wow.
Yeah, it forces very coarse category-level groupings. So this discriminative approach actively suppresses the fine-grained visual details you need for dense captioning or complex visual reasoning.
Because it only cares about the global representation.
Exactly.
Okay, let's unpack this with a visual for the listener. Traditional contrastive vision encoders are essentially acting like a nightclub bouncer checking IDs.
Yeah, that's a good way to look at it.
Right. The bouncer looks at an image and verifies, yes, this is a dog, or no, it's not a dog. It's just a rapid binary categorization.
Kind of binary, yeah.
But what your tech stack actually needs modern AI to be is an art critic. You want the AI to look at a painting and explain why the dog looks sad, or like how the directional lighting alters the mood of the room.
Right, and the bouncer simply lacks the vocabulary to pass those spatial nuances to the language model.
Exactly.
The bouncer is only trained to verify the category label, so the underlying math inherently flattens all those subtle spatial relationships that the art critic requires.
Just strips it all out.
Yeah. And if the vision encoder is only sending these really coarse summaries to the language decoder, the entire system just hits a hard ceiling.
Right. I mean, it doesn't matter how many billions of parameters you add to the language side, the input it receives is already fundamentally impoverished.
Exactly. So to bypass the bouncer, the Penguin VL team took a completely counterintuitive route.
This is the crazy part.
Yeah, instead of using a traditional vision encoder like CLIP, they initialized their vision encoder directly from a text-only large language model.
Wait, really?
Yeah, they took the weights from Qwen 3-0.6b. They literally grabbed a brain trained entirely on text and rewired it to process pixels.
Wait, here's where it gets really interesting, though. If you force a 1D token stream engine to process a 2D spatial coordinate system, don't you just destroy the LLM's architecture?
Well, that's the massive architectural hurdle they faced.
Because text models use causal self-attention, right?
Yeah.
They only look backward at previous tokens to predict the next one.
Right, because we read sequentially.
Yeah. But an image isn't a sequence. You have to process visual context up, down, left, and right all simultaneously. So how do they keep the language model from just collapsing when they mess with its attention mask?
That is the core technical magic of Penguin VL. They had to systematically unmask the model.
Unmask it. Okay.
Yeah. First, they transformed that causal self-attention into full bidirectional attention. They basically removed the algorithmic blinders. Yeah, allowing the text model to process visual tokens symmetrically, so it can see the entire image context at once, rather than treating pixels like a sequential string of words.
Okay, taking the blinders off makes sense conceptually, but what about the spatial geometry?
Hmm.
Because standard text embeddings just count position in a line, token 1, token 2, token 3. If you feed it an image, how does the model know that patch A is directly above patch B
Yeah.
rather than just next to it in a sequence,
Right, so they solved that by integrating 2D rope B.
which stands for two-dimensional rotary positional embeddings, right?
Exactly. Let's look at the math intuition here. Traditional 1D rotary embeddings inject positional information by rotating the token representations in a complex plane based on their sequence index.
Okay.
But by moving to 2D row P, the model applies independent rotations for both the row index and the column index of an image patch.
Oh, I see.
Yeah, this allows the model to dynamically encode the exact X and Y coordinates.
Meaning it can natively handle different image sizes
Yeah.
and aspect ratios without having to artificially crop or squish the input data.
Exactly. And during the initial training phase, they introduced this novel relation loss.
Relation loss.
Yeah, this mechanism basically forces the unmasked, spatially aware model to really pay attention to how different visual patches relate to one another. So it's actively teaching a text-native architecture true spatial awareness.
Wow. So if you're building with these models, the massive takeaway here is native alignment.
Absolutely.
By reusing those LLM weights, the vision encoder and the language decoder already share the exact same semantic space from day one. You just bypass the modality gap entirely.
You do. The vision encoder basically inherits the rich semantic understanding and world knowledge that the text model already spent millions of compute hours learning.
That is so smart.
It creates a highly compact, efficient pipeline. But, static images are one thing. As we scale this up, temporal processing introduces a completely different bottleneck.
You mean video?
Video.
Yeah, video token overload is a massive problem. I mean, a video isn't one picture, it's thousands of high-resolution frames.
Right.
If you feed all those frames into a compact 2 billion or 8 billion parameter model, it should just immediately crash from memory exhaustion.
It absolutely should.
So how does Penguin VL handle extended video on these edge devices without, just melting the hardware?
So the researchers engineer a mechanism called temporal redundancy aware token compression.
Or TRA.
Right, TRA. So when you watch a video, the visual data is actually highly redundant.
Oh, sure.
The background usually remains static, and maybe only a single object shifts position across dozens of frames. So TRA dynamically allocates the model's compute budget by distinguishing crucial keyframes from intermediate redundant context.
Okay, it's like reading a comic book.
How so?
Well, when you turn the page and hit a massive, highly detailed splash page of a battle scene, you spend a lot of brain power studying it. That's your keyframe. But for the next few tiny transition panels that just show a character's arm swinging, you only quickly glance at them just to register the motion. You don't analyze every single pixel again.
That perfectly illustrates the concept.
Yeah.
And how the model actually does that mathematically is by calculating the semantic similarity between adjacent frames.
Okay.
It computes the cosine similarity between the embeddings of consecutive frames. And if that delta falls below a specific threshold, meaning the visual information hasn't really changed significantly, the model actively drops the heavy spatial tokens for that frame.
Wow. So what does it keep?
It only retains a highly compressed, lightweight temporal marker just to maintain the sequence of events.
So it's aggressively pruning the token tree in real time.
Exactly.
By dropping the spatial data where nothing new is happening, the compute savings must be astronomical.
They really are. The TRA mechanism allows Penguin VL to process extended sequences of up to 180 frames.
Wow, which is roughly equivalent to like a 3-minute video.
Yeah, and it does it highly efficiently, even on memory-constrained edge devices.
The theoretical design here is just incredibly elegant. I mean, bidirectional attention, 2D row B, temporal redundancy compression. But how does this lightweight architecture actually perform against the massive brute force models that are, dominating the leaderboards right now?
The benchmark data completely validates the approach. It's amazing. Looking at the Penguin VL8B model, it achieves best-in-class performance across some highly demanding tasks.
Like what?
Well, on Document VQA, which tests complex reasoning over scanned documents, it scores a 96.2.
Wow.
And on Chart QA, which requires interpreting numerical data and relationships from non-Euclidean graphs, it hits 90.5.
That's huge.
Yeah, it doesn't just compete, it actively surpasses leading models like Intern VL 3.5 and Quen 3VL in fine-grained tasks. And in long context, video benchmarks like NextQA too.
And the 8B model is still remarkably compact, but the paper also details a smaller 2B parameter version, right?
Yes. The 2B model is where the sheer efficiency of this architecture just totally reveals itself.
Okay.
Because if you analyze the BL-Link benchmark, which evaluates multi-image reasoning and general visual knowledge, the Penguin VL2B model achieves a 15.1-point margin increase over Intern VL 3.5.
Wow.
I mean, a 15.1-point jump at the 2 billion parameter scale is an astonishing leap in capability. It definitively proves that a generation-aligned encoder...
Huh. Okay, I can see you getting fired up over that 15.1-point delta.
It's just such a massive margin.
It really is. But for developers looking to integrate this into real-world applications, I feel like the paper's qualitative case studies are what really bring these benchmark numbers to life.
Oh, definitely. The qualitative examples showcase a level of synthesis that goes way beyond simple image recognition.
Yeah, let's look at a complex coding example.
Oh, that one is great.
They provided the model with a single visual prompt of a highly complex math puzzle, like a hard-level competitive programming problem.
Right.
And Penguin VL didn't merely use optical character recognition to just extract the text. It comprehended the underlying mathematical logic, formulated a dynamic programming solution, and generated flawless executable Python code.
All from an image.
Entirely from an image prompt.
Yeah, and synthesizing visual perception with formal symbolic reasoning is historically a major failure point for smaller models.
Really?
Yeah, because it requires the vision encoder to pass absolute conceptual clarity to the language decoder.
That makes sense. Another brilliant case study involved historical documents.
Right.
They fed the model an image of a highly degraded text featuring archaic, old-world typography, and it perfectly transcribed the text while maintaining the complex spatial layout like the exact structural integrity of the page.
And retaining that fine-grained spatial awareness is the direct result of the 2D ropey integration we discussed earlier. Yeah, if a model scrambles the layout of a legal contract or a historical manuscript, the semantic meaning is basically destroyed. So, proving that an encoder initialized from a text-only LLM can preserve that geometric fidelity is just a massive win for the architecture.
The deep analytics capability is arguably the most impressive one for me.
Oh, the chart analysis.
Yeah. The team provided a multivariate line chart spanning 50 years of data. And Penguin VL actively analyzed the chart, identifying global minimums and evaluating the relative volatility across different decades. It was performing high-level data analyst work just from glancing at a non-Euclidean image.
Because it's actively synthesizing multi-decade trends, not just extracting labeled data points.
Right.
And for a model of this size, that is a profoundly high-order cognitive task.
It really is. So as we synthesize the findings of this deep dive, the overarching takeaway seems to be that working smarter is far more effective than just blindly scaling up parameters.
Absolutely.
By flipping the script, by aligning the vision encoder with the generative architecture of an LLM right from the start, Tencent basically bypassed the discriminative limitations of traditional contrastive learning.
They really did.
They created a highly efficient, compact model that can run on edge devices, but punch way above its weight class in complex reasoning.
It fundamentally changes how we think about model initialization going forward. And, it leaves us with a truly fascinating, almost philosophical thought to explore.
Oh, what's that?
Well, if a text-only large language model can be so elegantly rewired and taught to process visual data with state-of-the-art proficiency, what are the architectural limits?
Oh, wow.
Right? Like, what happens when researchers try initializing these text brains with audio waveforms or tactile feedback or thermal sensor data for advanced robotics?
Yeah.
Are we rapidly moving toward a universal modality-agnostic digital brain that can simply plug into any sensory organ we construct?
That is incredible to consider. We started today by imagining fitting a world-class AI on your smartphone simply by teaching a text bot how to see. And Penguin VL showed us the exact architectural roadmap for how that is done. But it seems like teaching it to see is merely the first step of what this modality-agnostic approach can really achieve.
Well, thank you so much for joining us on this deep dive. And if you enjoyed unpacking this research with us, please make sure to subscribe to the show so you never miss an exploration into the future of AI. Until next time.